Hello, everyone. Thank you for joining us today for the fifth webinar of 2022 Indian Energy Minerals Forum. Today's topic is helium and other rare earth elements on Indian lands. This webinar is being hosted by the United States Energy Association in cooperation with the U.S. Department of Energy's Office of Fossil Energy and Carbon Management and Sagebrush Hill Group. A quick note about the program that we are hosting this under. We are hosting this under the Consensus Program, which is a cooperative agreement with DOE's Office of Fossil Energy and Carbon Management that seeks to educate the public, policymakers, industry, and other stakeholders and builds a consensus on the benefits of and requirements for carbon capture, utilization, and storage, and other carbon management technologies. Think of methane emissions mitigation, carbon dioxide removal, as well as today's topic of rare earth elements, critical materials and minerals, and the like. Basically, if it falls under the purview of FECM, we help them disseminate information about these topics. We do this through a series of activities such as briefings and webinars like today's. We will have workshops throughout the year. We produce a number of studies, reports, white papers, and then we also have a monthly news clips to help keep our stakeholders informed. If you'd like to subscribe to our mailing list, please email my colleague Michelle Littlefield at mlittlefield@usca.org. Just a quick logistics reminder, all of our attendees are muted. This meeting is being recorded and we will post the recording onto our event page on usca.org/events. If you have any questions or comments, please use the Q&A box and we will do our best to address as many as we can. We've got a packed agenda today. Some really great high-level speakers who are really excited to hear from. And with that, I'm going to pass it over to USCA's Acting Executive Director, Sheila Hollis, to give a few introductory remarks. Sheila, the floor is yours.
Thank you so much, Alex, and it's a pleasure to be with this esteemed group of experts today and with our listeners too, participants. I'm Sheila Hollis, and I'm Acting Executive Director of the USCA. I wanted to tell you a little bit about USCA for context here. It's an organization that's about 100 years old. We're nonprofit, non-lobbying, nonpartisan all the way. We were formed back in an era when the primary focus was on electricity, the provision of electricity to the market, and it provided a forum for people to speak about it, people interested in it, but then it expanded dramatically. And on our board now, we have representatives of natural gas, coal industry, nuclear, hydro, renewable power, and a variety of other players, including academic institutions, the national labs, and the like. So we have, again, nonpartisan, nonprofit, a non-lobbying organization. We work all over the world, 104 countries. We work with USAID, the State Department, and the Energy Department on a variety of projects. We work with the states and we work with them closely because obviously the state agencies are nonprofit and work with us. We do programs that may be of interest to you. So if you check out the USCA website, usca.org, you will find out a lot more. I'm delighted to have this very august group. I've worked and lived extensively in the West, where a lot of the topics arise today in New Mexico and Wyoming and Colorado. So it's a pleasure just from a personal standpoint, as well as from a substantive standpoint for our audience, to have you with us today and hear what all is going on with respect to their efforts to improve carbon capture, to deal with the issues associated with all of the activity that has taken place, particularly in the West, but not exclusively over all these years. So with that, I turn it back to you, Alex, and on to Michael.
Thank you so much, Sheila. Next up, we have USCA Program Director, Mike Moore.
Okay. Alex, thank you, Sheila. Always great to have you as we kick these things in. And Derek and Steve, it's always been a pleasure to run with you guys. Known them for a number of years and always find great people to come and populate your programs with. Rare earth elements, helium, hot topics. Don't need to spend much time on that. We're going to hear that from the experts. But Derek and Steve, thank you again for the work that you do so we can put this up here with your group. So with that, I'm going to turn it over to you, gentlemen.
Thank you, Mike and Sheila and Alex. I'm Derek Watchman, and I'm president of Sagebrush Hill Group LLC. And Steve Gray and I are very honored actually to be a part of this program. And we're, as Sheila said, in conjunction with the United States Energy Association and the Department of Energy. Because I got a big truck outside here. And so we are delighted to have this outreach on tribal energy. And, you know, in my years of experience running energy, in many cases, the tribal component is not necessarily considered or included. And so I'm happy at the Department of Energy and USDA have asked us to do this outreach. And so our primary function for these programs is to disseminate and draw attention to the different facets of tribal energy development. And when you look at information out there on many fronts, there's significant resources that tribe use for energy, for resources. And basically the bottom line is that tribes not only are governments, but are businesses, and their task is to provide revenue to run tribal government, provide services to the people. So energy has been, for the most part, a mainstay for many of the tribes. And so today, as you'll hear, we're going to talk about rare earth minerals and helium. And so we have a great lineup. And so I'll turn it over to Steve for his thoughts. And so Steve, the floor is yours.
Okay. Good morning, everyone. Thank you all again for joining us on this series of rare earths and helium. We're very pleased to have everyone joining us today. As we have mentioned, as this transition continues to occur, especially across tribal lands, people are constantly looking for what are opportunities, what are our options out there, particularly tribes and the tribal community. And many of them are fossil fuel energy communities, as you know. For decades, many of them have relied on that source. So as we start to expand and do this energy transition, you know, many of the tribes are very concerned about the economic impact to them. These fossil fuels for decades have provided the revenue for their tribes to run their governments and to provide service to the Indian people. And then it's also provided good jobs. And many of these good paying jobs are in rural areas. So now as this transition starts to occur and people look at other options there, you know, one of the things that comes up always from the tribal communities is what is the economic impact to me and my people? And so we're very pleased today to have our guests joining us today to talk about some of those options, talk about what others are looking at and what opportunities are there that they could also start to examine those options as well. So with that, we're very pleased everyone's here to join us, and we look forward to hearing from our speakers today. So with that, I'll turn it over to Derek to welcome our first guest speaker. So go ahead, Derek.
Thank you, Steve, and my apologies. I'm up in Spokane today. I'm at a hotel, and all of a sudden there's a big old tractor or something outside, so bear with me. I'd like to introduce Stephen Atha, who is with Stephen Atha Consulting LLC, and he's a retired attorney with over 40 years of experience and has worked largely with the government, U.S. Forest Service, Department of Defense on many fronts. And so Steve has worked on the independent buy side, working under contracts. He's a shareholder and a senior advisor to Critical Minerals LLC, an affiliate of Great Plains Partners Venture Capital, or Venture Group, excuse me, He's a graduate of Washburn University and Washburn University School of Law. And so Steve, welcome. And we look forward to your presentation. So I'll turn it over to you. Steve, thank you.
Thank you, Steve, and Alex, and Michelle, and Derek, and all of you who've allowed me an opportunity to speak to you today. Actually, you didn't invite me to this session. You invited Bob Happany, who is the managing director of Critical Materials LLC, and he had another commitment and asked if I would fill in for him and speak on what I knew about this topic. So in a sense, you're all getting the substitute teacher here today, and I would ask you to grant me a little leeway and cut me some slacks in case I misstate something. I'm being followed by an associate of ours at Sandia National Laboratories, Mark Regali. So I hope Mark will correct me later on as we go on, but not pointedly as this is happening. Let me give you a little bit of background on Critical Materials LLC. It's a New Mexico LLC, recently formed primarily to work in conjunction with Sandia National Laboratories' recent discovery of interest to us in the critical materials field. Critical Materials is affiliated with an earlier corporation called Great Plains Partners Venture Group. It's based in Kansas, and it was started by a number of, along with Bob Happany, a number of retired military people and consultants to the military and industrial supply chain in various ways. Bob, by way of background, is a former Lehman Brothers partner, dealing with investment banking in all fields internationally, and had a distinguished career there. Through chance, he made it to Kansas, and he had had a vision on how to make use of his business model that he developed over years, working first with clients such as Ford Motor Company, and then with a consortium of universities in New York State through their pension plans to invest funds into emerging technologies that weren't being exploited. Initially, but what Bob was talking to Ford Motor Company, we're going back 30 years now, and they were on a quest to lower the weight in vehicles of all types. And they asked him if he could come up with some technology that he'd run across to lighten the weight on brake rotors for cars. And as chance would have it, he knew of development in that field, and started a little small company and licensed the technology through a technology transfer with the inventors, and commercialized the technology by creating prototypes, which satisfied Ford Motor Company's requirements. And one of their major suppliers of components, Bendix Corporation at that time, was very interested in sharing in that business, and they in turn licensed it to them as well. And eventually the material, lightweight metal, which was stronger and lighter than the conventional steel that was being used, made it into all the Ford Motor Company products. And he duplicated that model on behalf of the university systems. And in the course of about 5 years, he created 50 small corporations, LLCs, and hooked them up to university laboratories and national laboratories, and found technology that could be developed and commercialized. And in the course of 5 years, they sold 40 of those small companies to larger entities who were regular suppliers to major manufacturers and defense industry supply chain members. And about 4 of them, I think, went kaput, and 4 or 5 declined to sell. The owners wanted to keep running it as a small business, and they did. But it was a pretty good track record and a model, and that's what's being modeled in Critical Materials LLC. If we can go to the next slide, Alex, if you would. Okay, this group is a venture capital group. I don't think I have to, well, there won't be any math in my presentation as compared to some of the others going forward here. It's mainly just my thoughts and collections of materials, and partly based on the PowerPoint presentation that Bob Happany usually presents in a financial setting. But what is critical materials, and why are they critical? We have definitions of that come from the federal government. I think we are aware of the supply chain issues that the country's confronted with, particularly in the area of microchips and how that's influencing auto production. Well, all aspects of our economy are being affected by materials that are sourced other places, and we have disruptions in them. So if they're critical, it means it's what's necessary in order to maintain our #1 national defense and our strategic security as a nation to continue to function. So those things change over time. So the answer of what are critical materials, it sort of depends on the era we're in. Why are they critical? It's because we have, in the last 20 years, outsourced most of our production of a lot of things that we depend upon to keep our economy flourishing and to provide for our national defense. And you might think it's strange, I do, that we have, in large part, transferred our capabilities for critical materials that we were dependent upon to our chief adversary, China. And that's not a good situation, and it gets recognized. It's recognized today, but it's been recognized over history. If you can just flip to the next slide for me there, okay? It may come as news to you that we've had a strategic critical materials stockpile in the United States officially since 1939. That coincides with the German invasion of Poland, and the Defense Department at that time, then called the War Department, and the administration under President Roosevelt recognized that we're dependent on foreign sources for a lot of the things we need in order to defend the country in World War II. And so they started at that point with a national defense, well, it's all called the Strategic and Critical Materials Stockpiling Act. So we had stockpiles of critical materials, and there were hundreds of them at that time, including a lot of things we no longer find critical. So this changes over time. But I'll just read you briefly what the purpose of it was. It's just been renewed again in 2019 in the Trump administration, and it can be found at 50 USC 98. And it's a congressional finding and declaration of purpose. The Congress finds that the natural resources of the United States and certain strategic and critical materials are deficient or insufficiently developed to supply the military, industrial, and essential civilian needs of the United States for national defense. It is the purpose of the act to provide for the acquisition and retention of stocks of certain strategic critical materials and development of the materials within the United States domestically, and therefore to decrease and preclude, when possible, a dangerous and costly dependence by the United States upon foreign sources of a single point of failure for supplies of such materials. So in the context of World War II, they started building up stockpiles and of various commodities. And there were things that you would be surprised today to learn that were in that program, but the chief ones were manganese and chrome ore, which were used in steel production and necessary to build tanks and trucks and all that sort of thing that was ramped up during the beginnings of the war. And but they also had a lot of other things like bauxite, which we depend on sources in mainly Jamaica for the bauxite. The chrome and manganese largely came from Africa, and with the Navy, the German Navy patrolling and jeopardizing shipments, we felt very dependent on those, and were fearful that those supplies could be interrupted. We also had lead for bullets. We had copper, of course, tin, zinc, asbestos, which is not valued now. It was in those days as the fireproof insulation around boilers in ships worldwide, and sourced largely, some from Canada, but largely from South Africa. But there were other things like talc and crude rubber and well, even sperm whale oil, which was used in, I think, in bomb sites at those days. It didn't freeze up and thicken like other oils did. So it was valuable, and there were drums of that stockpiled. At the peak, this all valued at about $11 billion in those days. It would be more than that today. But as over time, they never achieved the stockpile goals that they wanted to achieve during the war, and then just continued to add it back up afterwards. I think Eisenhower's plan was that we should be able to sustain ourselves with our stockpiles for a 5-year land war in Europe, contemplating war with Russia at some point, which is now occurring in a de facto way. But at the peak, there were over 300 stockpile locations around the country. They were at military bases, industrial sites, and now we're down to about 3 or 4. They've sold off the stockpile gradually as they saw that we didn't need it anymore, or sometimes it was for financial reasons, or there were political reasons why it happened. But all these factors intervened to reduce the stockpile down to where there's only about 3 or 4 sites. There is one in Arizona, as a matter of fact, still existing in a little town of Wyndham, Arizona, which in the West you may be familiar with. And it consists totally of manganese nodules. It's manganese ore, but not mined. It's laying on the desert floor. And the story I've been told over the years was that the local residents in the area, probably many Indians at that time in the 40s, 50s, 60s, supplemented their income by picking up manganese nodules and trucking them to Wyndham, where they were stockpiled. That stockpile still remains, but the others are much depleted. Among the other things that were in the stockpile were some rare earths at that time, rare earth elements, notably monazite sand, but also which is a thorium ore, and also cobalt. Lots of other substances were there, and I handled those. How I came to get involved in this was that in the 70s, I worked for a company that contracted with the at that time General Services Administration, which handled the stockpile, to handle the receiving and shipping out as materials were sold at various locations. And at the high point, I think we had 17 or 18 contracts in about, or 30 contracts in about 17 states around the country, where we handled the material, loading it onto trucks, rail cars mostly, sometimes transporting to ships for sale as they sold off the stockpile. My first involvement with rare earths was that there was a stockpile of monazite sand at the Great Lakes Naval Training Station up in Wisconsin. And they sold it to a South American mineral company. And we, in a very crude fashion, loaded the material into steel drums, labeled them radioactive, loaded on trucks, and shipped it out. And monazite sand is a kind of an orange colored beach sand, but commonly found in India and lots of other places. It's only mildly radioactive, but it was useful in the development of the extraction of radioactive isotopes that were valuable at that time. And we've got other sources of that now. Uranium was in short supply, and I won't have to go into all of that, but if we go to the next slide, this is the periodic table. You'll recognize this, and I'm not a scientist. I'm a lawyer by training, but it does. I guess the reason for showing this is to get some kind of definition of what rare earths are, and they are, of the elements that are depicted here. Of total, there's 118 known elements right now. At the top left corner, you've got H, which is hydrogen. And on the top right corner, you've got helium, which is, or He, helium. If you subscribe to the Big Bang Theory, you think that initially there were two elements, hydrogen and helium. The atomic weight of hydrogen is 1, and the atomic weight of helium is 2. And those formed everything. And then I don't know that much about helium, but I do come from Kansas, and that's a state which was known as the largest deposit of helium for many years in the southeast corner. Helium is a byproduct of natural gas, and the story goes that in, I think, 1906, oil and gas driller was discovered this gas was in sufficient concentrations coming out of a supposedly natural gas well that wouldn't burn. And it's because it's an inert gas, and that was recognized for the first time that this was useful. And it's useful in a lot of ways. All of these elements are in the things that are listed right here in the manufacture of wind turbines, electric vehicle batteries, cell phones, computers, MRIs, all kinds of equipment, where helium in particular, because it's an inert gas, allows for a controlled environment for this and for the development and production of these products. The other individual products have other uses, but and here, let me give you another basic one. If you're a layman like me, you wonder, rare earths. Why are they called rare earths? Well, they're not particularly rare. They're all over the world and dispersed throughout the Earth's crust, but they don't occur naturally. They're usually bonded with another, or alloyed to another metal product, and only in the process of extraction or heating are they identified and recognized as an independent element. And so the 17 rare earth elements that are there have been extracted by and large by a process that was interests me a great deal, and why Critical Materials LLC came into being. I read a lot of obscure science things and other blogs and things, and a few months ago, well, a year ago now, I guess, I happened onto a science magazine blog entry announcing a new discovery at Sandia National Laboratories regarding the extraction of rare earth elements from coal fly ash. And the conventional method to do that used very caustic acids and produced the kind of problems largely that were caused the closure of the mine at Mountain Pass we talked about in California. It's a nasty byproduct, and it's hard to handle. But anyway, these two young researchers, Mark Regali being one of the presenters, is one of the co-inventors of this process, and his associate Gangping Zhe, I'm probably mispronouncing it, but they invented or discovered another process for extracting rare earth elements from what is ordinarily a waste product, coal fly ash. It's a disposal problem. That intrigued me. I thought it was revolutionary. So I contacted Bob Happany immediately and said, you need to get down to Albuquerque and talk to these guys and see if this is as earth-shattering as I think it might be. It's revolutionary, and I think it bears examination for a possible investment and see if they want to develop it. and they'd applied for a patent for it. And so Bob did, and formed a close association with them and talked to their tech transfer people and began to implement the critical materials model of development that I talked about a little bit later. That's how we got to the point where we had a real abiding interest in rare earths, which I'd been involved in since the 70s off and on, but was a new item. So if they're not that rare, but why do they call them earths? Well, when the first element was discovered by a black rock by a geologist in, I think, Norway in 1786 or something, he couldn't identify it, but he broke it down and with acid and found a new element, which he named yttria. And then there's 3 or 4 other elements that have come since that, all yttrium, and they all begin with YTT, based on the little town that this gentleman was from. And there's obviously more than 118 elements, because there were only like 86 when this, 25 years ago. we keep discovering new ones. That's the marvel of our scientific establishment. They're able to come up with new ways to discover things that have been there all along. But that explains why I'm interested in critical materials. If you go to the next slide for me, Alex, would you please? Critical supply chain problem. Okay, well, here's the problem. China controls 90% of the rare earth minerals market, and we're dependent on them, puts us at a competitive risk. And China is capable of weaponizing the supply chain, thus threatening our national security. And they've done it in the past. It's not like this is a new idea. They did it in 2010 in a dispute with Japan because some Japanese forces falsely detained a Chinese fisherman somewhere. And so in protest, they stopped shipments of rare earth materials to Japan for a period of time. And they also did an embargo in about 2010 or 2011, which drove the prices of rare earth elements up through the roof. There's a graphic on that coming up here somewhere, but it's very easy for them to withhold it because they have a stranglehold on the market for it right now, which is why it's critically important that we develop capabilities domestically to produce and extract, to produce the ore, safely extract the rare earth elements, and get them into industry that we can control on our own without being dependent on our foes overseas. So if you go to the next slide here, please, the solution. Okay, well, I've explained to you how and why I got involved in this and why critical materials is focused on it. Right after we'd talked to Sandia, shortly thereafter, other articles started appearing on rare earths. And I'm going back about a year and a half here. And I use in my business Google news alerts. I don't know if many of you do or not, but you might if you haven't already. They're free. If you have a Google account, you can sign up for news alerts on any particular topic you want to. And rare earths is one that I plugged in right away. And a year and a half ago, I would get typically 4 or 5 articles from around the world sent to my email box daily. Well, maybe a week. In the course of a week, I'd get 4 or 5. Today, I'm getting 20 to 25 per week, per day. And they are, I get 2 dumps, one in the morning and one in the afternoon or evening, that all the mentions of rare earth elements. Right after we met with Mark and his team in Sandia, Forbes magazine put out an article about this, how these inventors in Albuquerque had come up with a way to extract rare earths using orange juice or Coca-Cola. And it was sort of a throwaway line, but it's not far off. Mark will go into more detail about how that happens. We go to the next slide. I think that explains the process and the award that they received. And if we go, let's skip over the next slide, critical materials. Let's skip that one. I'm running out of time, I think, here. Sometimes people finish listening to me before I finish talking, and that may be happening here. But anyway, critical materials recovery. This is basically just to show the types of materials that Sandia is working on extracting: coal, coal ash, and shale. I'll skip over the next one, critical minerals recovery. I think Mark's going to cover that as well too. The next one, even I'll skip over it. It depicts the rapid, that spike there is showing when China put in export restrictions and what it did to the price of one particular commodity. And note that these are prices, dollars per kilogram. So I'm used to dealing in tons. And so you multiply that by 1,000 at 300 and some dollars per kilogram, you're talking real money then when you get there. And so our solution is, go to the next slide, please, Alex, is we solve with our model and others are doing the same thing and have been doing in other fields, agriculture and others. But this is a reality. There's what's called the valley of death for funding of technology. And the federal labs and the universities' research teams have all kinds of technology that's been paid for. There's a lot of money that goes to the development of new technologies, but when it's completed and the project's over, it goes on the shelf someplace because there's no funding to develop it and commercialize it. There's demand from the corporations on the other side. So our model for Critical Materials LLC is to fund through a combination of federal funds. Flip to the next slide. There we go. We're going to leverage grants, government grants, and venture capital money in order to fund the developing prototypes and actual production runs so we can commercialize this technology and make it real. And that's what we do. I appreciate the opportunity to talk about something that I don't know how widely the interest is. I've run out of time. I have some thoughts about helium too, but I'll save them for another time if we can. Have I run out of time, Derek, or not? Do I have a minute?
I'll give you another minute, Steve. Very, very good overview, but I'll give you another minute.
Okay, well, helium, there are large, I'm from Kansas, and we had one of the largest helium deposits in Kansas in the Hugoton field, but there are large deposits in the West, as you said, in Arizona in particular, up in the northeastern corner of Arizona at the, I'm going to say this wrong, Pinta Dome, I think, area. It's in Apache County. And what's unique about the helium deposits there is that helium is generally considered they'll go into an old abandoned shut-in well, natural gas well and produce the helium from it. And it's commercially feasible at 0.3% helium. But the deposits that they have in Apache County measure 5 to 10% helium, pure helium. So it's much more economical to do. And you are on a valuable resource compared competitively to other places. But thank you for your time. I appreciate it, and look forward to hearing the other presentations.
Likewise, thank you, Steve. Great overview. And basically that's what we're trying to do is discover and look at all the information that's really pertinent to Indian country. So next, I'd like to introduce Marty Williams, who is the president of American Rare Earth Limited. And Marty and I just got introduced to each other, but Marty has been involved on many, many activities looking at critical minerals development, materials development. He's a global executive with a master's and a master's in science from University of Tennessee. He's been involved in IT, artificial intelligence, healthcare, and has been looking at many opportunities in the country relative to rare earth and particularly on opportunity zones. So Marty, I appreciate you joining us and I look forward to your presentation. So the floor is yours, sir, and welcome.
Yeah, thank you, Derek, and thank you to everyone here, attendees, and the other presenters. So always something good to learn from these. So I'm with Western Rare Earths here in the U.S., our parent company is American Rare Earths, which is an Australian publicly traded company. And my should have updated the date on my slide here. Because our parent company is publicly traded, we have to give a disclaimers and forward-looking statements up front. I like to say this is mainly to tell you that half of what we think we know is wrong, and we don't know which half, but we're trying to figure it out. So, everything in this presentation started with someone else. This is, I'm not a principal investigator. I'm not a primary researcher, but am someone trying to pull together this supply chain domestically. There is a trigger warning here. There's going to be some math. It won't be too difficult though, but it's always good to let folks know it's coming. I like beginning with the end in mind, and so here's the summary before we even get to the end. Basically rocks are hard, and and rare earths are more difficult. So to be able to onshore the supply chain, back from the Chinese, as described earlier, we're going to need better processing technology, and we're going to need a lot of smart people, and we think we have a path to getting both of those things pulled together. Permitting of mine in the U.S. it's not just hard; it's ultra marathon hard, and we believe that the traditional extraction, separation, purification of rare earths is a pretty nasty business. So we're not interested in traditional technologies. We're so much we'd really like to onshore supply chain that involves not just extraction, but also separation and purification of rare earths in a way that's more environmentally accountable, as well as water sparing, renewable, and sustainable. So now that's easy to say and is extraordinarily difficult to actualize, but we think we've got a good running start on that. So this is covered previously a little bit of what are critical minerals, what are rare earths, but essentially critical minerals as defined by the government is now a list of about 50 minerals. These are non-fuel minerals essential to the economy and defense. Rare earths are a subset of that, and you gave the periodic table previously, so you saw the 15 lanthanides at the bottom, plus scandium and yttrium. But we think the bottom here is really the critical piece of this, that solving the shortage of critical minerals is going to involve more than just exploration, mining, and processing, as well as recycling, but there's going to have to be some changes in permitting while still protecting the environment and communities. And it's more about not getting rid of rules, but making it possible to not get hung up in overlapping and redundant rulemaking and processing. So all the rules are relevant. It's where they overlap and become redundant and therefore get stuck on top of each other is where the challenges come in. So why are rare earths critical? And again, this is practically and politically the demand is increasing. Current suppliers and processors are countries with unacceptable political risk. You're mainly talking about China, Myanmar, Russia. So those are folks don't always have our best interest at heart. We believe there's political will to promote the domestic supplies, but then what's that look like on the ground? So that's a little tougher to sort. So I'm going to simplify really the economic drivers around rare earths. While there are 17 elements in what we call rare earths, the economics really come down to 4. Those are neodymium, praseodymium, dysprosium, and terbium, and they're used to make magnets, these high performance permanent magnets. And why do we need magnets? The magnets really come down to motion and electricity. So in a reduced carbon, new energy future, transportation gets electrified, and the grid and everything. We electrify as many things as possible, taking carbon-based fuels out of the system. So if you see the top, the block on the left there, transport type, traditional propulsion system, which is an internal combustion engine using gasoline. That's where we are today. As we electrify transportation, and this could be either battery electric vehicles or even hydrogen powered or fuel cell vehicles. All of those are ultimately creating electricity that goes to an electric traction motor to make the wheels go round. So those motors, those electric traction motors, require rare earth containing permanent magnets. So the simple way to think about this is, if you have electricity and you're trying to turn it into motion, you need rare earth permanent magnets to do that. The reverse is also true, to turn motion into electricity. So that would be a wind turbine, whether that's especially an offshore wind turbine. So the wind turbine turns, that's the motion. Turn that into electricity, you need these rare earth permanent magnets. So typically, in looking at any, let's say in Indian country, there's a rare earth deposit, and that might be coal associated, or it might be a standalone, rare earth deposit that could be a mining opportunity, or even in a waste pile or a fly ash pile, whatever that might be, whatever the source content might be, where those rare earths might be held. It really comes down to 4 of them that are used to make these magnets, are probably 90 to 95% of the economic opportunity that is within any rare earth source. And to understand kind of the, where does the metal make a difference? If you look at the box on the right there, ICE is internal combustion engines or vehicles, and then on the right is a battery electric vehicle, and you see the mineral content per vehicle. Now that's not just rare earths, that's a number of things like copper, lithium, nickel, cobalt, manganese, graphite, but rare earths are a big part of that. So we need a lot more. The electrified transportation future needs a lot more metal, and most of that metal is going to have to come out of the ground somewhere, and that's ultimately that's probably a mining opportunity that includes rare earths as well as a number of other metals. So the math is coming. The math is on the horizon. I warned you about the math. So we think about this, the 5 dimensions of mineral availability. We ask these questions. We as a company, Western Rare Earths and our parent company, American Rare Earths Limited, we are a mineral exploration company. We're not a mining company. We don't dig big holes in the ground. We do the exploratory work to find significant deposits that have a economically development opportunity associated with them, and then look to bring those forward and doing the permitting, planning, engineering, and getting projects to shovel ready. So in looking at that type of opportunity, we look at these big 5 dimensions of geologic availability, technical availability, and of extraordinary importance, the environmental and social availability. If it's near really a sacred site, or if it's near residential area, that's probably not environmentally and socially available, no matter how good the deposit might be. So we want to be really sensitive to the environmental and social impacts of looking at any given opportunity. So, and then of course the economics of it. Is it worthwhile? Can it produce jobs? Is it sustainable for not just a few years, but for decades into the future? So, if we break that down, so we look at this as A, B, C, D, and E, and then you make that a math equation. So make any factor equal to 0 in this equation, and the product is going to be 0. So we can't just have part of this. All of these things need to be satisfied to the affirmative in order for any given mineral availability to be realized, in our opinion. So to give a little context here to the complexity of the life cycle of a mine and how that's changed over the years, prior to the 1970s and the reality of more interesting, more difficult economics, and the reality that all the easy mining has been done to a great extent. It's just more challenging these days. We're faced with the reality of the easy stuff has been found and been extracted. we're dealing with lower grades, lower concentrations is the reality we face these days, and higher environmental requirements, and appropriately so, in my opinion. So, in the 70s, you had the Environmental Protection Agency created by then President Nixon. So that created some substantial changes. And then as we come to the, into the 70s and the 2000s, therefore, mine permitting, environmental impacts, environmental assessments, reclamation, decommissioning, those things are all a critical part of the plan and have to be a part of the full life cycle plan of a given project. And that continues to grow. So this becomes an increasingly more complex, but as a result, much more responsible industry and much more accountable industry as a result. So. Just checking the questions there really quickly. All right, so challenges. So, it's easy to identify challenges here. I have a couple slides of challenges really quickly. How much do we need? Is there enough in the global pipeline? Can any of this stuff be recycled? Are there substitutions? So those are things we look at in this particular supply chain. But the really heavy one here, and I think certainly for this conversation, can it be done environmentally friendly? What are the reclamation challenges? What does the land look like while we're there, and what does the land look like 100 years from now after the extraction is complete and reclamation has been completed? So, if you look at traditional rare earths mining, extraction, processing, it's nearly always associated with uranium and thorium, which are both radioactive. So that makes people nervous, and that can be really challenging both to get permitted as well as, how is it handled, how is it managed. And, and the waste from mining such rare earths, will have to accommodate, both the radioactivity and then radon gas potentially. So our focus as a mineral exploration company has been to avoid deposits that are have significant uranium and thorium in them. So to give a metric to it, so think 500 parts per million. Anything above that, requires special handling, requires an NRC permit. We only focus on projects where both the deposit is under 500 parts per million, but also as we beneficiate and concentrate the material, that we remain under that veil of what would be considered requiring special handling. And it's, just no different than any other dirt you'd walk around on, as an example. So that's a key focus for us and our approach as we look to find projects that can be brought forward. Other challenges are, these can be price sensitive. It's easy when you're talking about a comparatively small market compared to, say, iron ore or aluminum or copper. These are really small markets in comparison. They can be really price sensitive. It's tough to find, long-term reliable buyers. Long-term buyers want a fixed price, but operating costs are variable. That's a struggle of the coal industry and long has been, as well as any other. Currently, globally, you've got several monopolies and oligopolies. So, for example, the Chinese control 60% of rare earth reserves globally. They control about 85 to 90% of the processing market. Well, all of that is concentrated with actually 3 companies, and those 3 companies, the government of China is the major shareholder. So ultimately, the government controls the strings on these 3 companies, which essentially function as 3 monopolies, one focused on light rare earths, one focused on heavy rare earths, and one focused on processing. So that creates a pretty easy control reality that can be cut off, as was explained a bit earlier. So And then also we look at, are these minerals conflict minerals? So in an example here, rare earths produced in Myanmar would be an example of conflict minerals, because Myanmar is definitely in conflict. So in conclusion here, we see right now an unsolved problem that needs many solutions. So, a new tech stack for sustainable, responsible processing. The people to do that, human capital to drive and scale that new tech stack. Permitting reform, and then, but we do believe that American mining remains the cleanest and greenest in the world. It's still tough business, but it can be done responsibly. We're really focused on the first two bullet points here, the new tech stack, and that's where we are as a feedstock provider are really partnered closely within the Critical Materials Institute and partnering with a number of the national labs like Oak Ridge, Lawrence Livermore, Idaho National Lab, as well as a number of universities, University of Kentucky, Penn State, Arizona State, University of Arizona, Columbia, and there's several more. I'm forgetting everyone involved, but looking at technology in several areas of this processing capability. So we believe there needs to be new technology not only in the extraction piece, but also in separation, purification, and in metal making. It's not, I've not seen one single technology that gets us from source to sellable product in a simple process that's scalable yet. So we think it's a pretty robust tech stack that's going to be interwoven with a number of existing traditional technologies as well as some emerging technologies, and we continue to look for those. We don't have all those answers, but we continue to look for them, and not only the technology but the people. So similar as before, these opportunities around funding with EERE, ARPA-E, the Department of Energy, DARPA, Department of Defense, they present opportunities to fund these research partners to do this work, and which also creates essentially paid training for those scientists, those researchers to become the future leaders and future staff that we need to operationalize that emerging tech stack. So, and that's it. I'll pause there for questions. That's my presentation.
Okay. Thank you, Marty. Very good overview coming from Western Rare Earths. Our next presenter, he comes from one of the Department of Energy's national laboratories. And Dr. Rigali, he is a principal member of the technical staff, and he came to us here in the Four Corners region talking about the rare earths opportunities and what they were looking at in some of the power plants in the region, some of the ash. And so it was very exciting, some of the science, cutting edge science that they are looking at right now. And we're just very pleased that Dr. Rigali could join us today and share his insight with what he's doing as well. So with that, we'll turn it over to Mark. You're muted, Mark. Unmute yourself.
Sorry, I thought we were muted on your end. My apologies. I'm Mark Rigali. I'm a research scientist at Sandia National Laboratories. Over the years, working on a variety of different challenges, a lot of it water treatment related, removing uranium from groundwater, things of that nature. So selective separation of metals and other contaminants from water. My background is geochemistry. I was trained as a geochemist at the University of Arizona. And I've had the opportunity over the years at Sandia to really flex and extend my educational background to get into doing some cutting edge interesting and very fun science and applied science and engineering. So I'm going to talk to you a bit today about the work and some of the technologies we're developing for mining rare earth elements and other critical minerals and elements from what we would call unconventional sources. And an unconventional source would be obviously something that one would not normally consider an ore. And in some cases, we're actually looking at what are commonly considered waste materials and turning waste into critical materials and doing it economically so that we can have our own processes and sources of rare earths, outside of the traditional mining arena. So next slide, please. So I just want to acknowledge folks, collaborators that we have and are engaged with currently at Sandia. Particular acknowledgement of Guan Ping Zhu, who started all this. He wrote a proposal called a lab-directed research and development proposal. This is money that's accessible internally at Sandia, where the DOE allows us to make investments in research in cutting-edge areas. He was successful in securing that funding, and that's what got us started. We've gone kind of way beyond what we started with in terms of the team, both internally, a number of contributors whose names you'll see listed there on the slide. We began collaborating with Critical Materials LLC, Robert Happany, who Steve mentioned, Steve himself, and Critical Materials has begun to staff up, as it were, bringing in folks to help on their side to collaborate with us for moving from a TRL of 4 to TRL 6 and beyond. So we're working with them to get across the gap there, the valley of death, as they call it, to move something that's very promising in the laboratory to an actual commercial venture and process. Also have had engagements with USA Rare Earths, who have the rights to the Round Top deposit in Texas, which is a very interesting primary uranium, primary rare earth element ore body down in the El Paso area. So this is a group, and we're always willing to expand this and bring on other collaborators. There's a lot of work to be done. There's a lot of opportunities in terms of accessing and mining these unconventional sources of critical metals. Next slide, please. So I'll go into a little more detail fairly quickly about what critical materials are. This is a list of 35 critical materials that the U.S. relies upon, and a vast majority of them were 100% dependent on a source from outside the United States. And you'll see China show up fairly frequently in the list. This does present some not only economic security issues, but national security issues, because we at times have an adversarial role with them. So the rare earth group is mentioned. Another one I wanted to call out in particular is scandium. It tends to be grouped with the rare earths. It tends to occur with the rare earths, but it doesn't. It isn't officially a rare earth element, but I call it out because it's highly valuable. $1,000 a kilogram currently on the spot market for rare earth metals. Others that were mentioned: cobalt, chromium, vanadium, and there are a number of these that we think we can access and develop with some of our technologies, and access these metals in what would normally be considered unconventional. So let's go to the next slide. Whoops. Oh, so a quick note about the rare earths. Not all rare earths are equal. Some of them you can are in the thousands per ton or hundreds per ton, and some are dollars per ton. And so the list there you have of the critical rare earths that we're focused on are some high dollar rare earths that we are finding in quantities in sources like coal fly ash. Next slide. Yeah, so here's Steve's periodic table again, and highlighted on the left there are a number of these rare earths that have fairly significant prices per kilogram. Scandium is interesting because not only is it's an alloying agent to strengthen light metals, so it can show up in the metal frame of a mountain bike, and all the way to a number of different defense applications. That's one of the reasons why it's in very high demand. So they're not only are there applications and uses for it in things like sporting goods, but you go all the way to sophisticated military defense systems, and that makes it highly valuable. Neodymium, Marty mentioned before, again, relatively high price per kilogram, and another one that's in fairly high demand, and it shows up in a lot of different places from magnets, and these magnets can be in cars. They can also be in defense systems, missile systems. So it's another one that has a broad set of applications and is very important, both commercially and militarily. And so and a list of others: terbium, dysprosium, and yttrium. And I'm going to mention scandium, neodymium, and yttrium because we actually find these in some of our unconventional sources, and at their dollar values, we think we have an opportunity to mine things like fly ash economically. And so scandium, neodymium, and yttrium, if you put it together, it spells Cindy. So we're looking for Cindy in fly ash and other sources, as I'll mention. Next slide. And again, this is just emphasizing all of the different places the rare earths show up, and how critical they are, not only to our energy future, as Marty nicely pointed out, but electronics. Europium makes the phosphors in your television red, and so they show up in all kinds of different places, from your television set to light bulbs, to, you know, top high-end defense and you know, military applications. So they're very important to our economy. And the way I liken it is, I would say they're critical not only to our economic security, but also to our national security. Next slide. Next slide. Oh, one point on that previous slide, you don't have to go back. One of the things that's very important to note in all of this is, and Marty also made this point, we expect a considerable increase in demand over the next 2 to 3 decades. So we as a country are not producing much in terms of rare earths. We're behind, and we're only going to get further behind as time goes forward. So we need to have alternatives and alternative sources that we can rely upon if China invokes another trade embargo, or we just competitively don't have an access to the materials the way we need them for our economy and defense. So traditionally, there's open pit mining, and you can see an example of that on the bottom right. That's actually a picture of the Mountain Pass uranium, or excuse me, rare earth element ore deposit. And as Steve says, or excuse me, as Marty said, there is uranium and thorium that occur in this deposit, and one of the challenges and costs is managing that thorium and uranium stream. So the picture on the right is somebody that's in China, and they're working the what look to be the heavy rare earth element clays. So China benefits from having unusually large deposits like Mountain Pass, but they also have rich deposits in the heavy rare earths, which are the ones that tend to be more expensive and more important in these what they call heavy rare earth element clays. So they've got it all right now, but I think we have not only the sources but the technologies to create our own domestic supply. Next slide. So I'm going to get a little bit more detail into what I mean by these unconventional resources. We've been looking at the extraction of rare earth elements from coal, potentially before it is consumed in a boiler to make energy. Even more interesting and important, we think, is processing the coal ash. The coal ash is basically the residue that's left over from burning coal to produce energy, and it has a number of advantages to exploit as a potential resource for rare earths, because it's concentrated. Because it's coal residue, the rare earth element end up being concentrated potentially by an order of magnitude or more in the coal ash. And shale, which I'm not going to say a lot about today, but that's something we're actively exploring. And by that, I mean taking advantage of unconventional oil and gas production in shales and post oil and gas production, there may be the opportunity to use our extraction process to extract metals, transition metals, rare earth elements, possibly platinum group elements as a source, so that we can take advantage of the fact that the existing infrastructure is already there. We'd be using existing oil and gas wells and going in before they do plugging and abandonment at the end of the oil production process, and mine these shales for critical minerals. So focusing in on the coal ash opportunity, there is a lot of coal ash that's out there and available. And there's growing concern over these impoundments and piles of fly ash that are sitting next to power plants all over the country. So this represents a tremendous opportunity for mining rare earth elements with a material people consider a waste, and to some of the power plants, this is actually a liability, because eventually they're going to have to do something about cleanup, and that in and of itself, I think, opens up an opportunity for us to extract rare earth elements, and then potentially sell the cleaned coal after we've done coal ash, the clean coal ash after we've done the extraction as a product for, including cement filler materials, and maybe if we can clean the ash well enough with our process, it could potentially be viable for fertilizer applications down the road. So we're not just looking at coal ash as a source of rare earths. We're looking at other value-added opportunities for when we process the coal ash. We're utilizing it to the fullest extent. Okay, next slide. So I don't have any pretty pictures of our lab equipment, but I'll just describe this process and how it works. We talked about CO2 and the use of supercritical CO2 in this process. What we do is we have a citric acid, and citric acid, as Steve mentioned earlier, is something all of us eat every day. So it's in all kinds of products, from oranges and lemons and any kind of citric fruit to numerous products in your refrigerator. It's a flavoring agent for sour candy. There are a lot of, it shows up in a lot of places. It's non-toxic, environmentally benign, and it makes a great agent for helping us to extract the rare earth elements out of the coal ash. So what we do is mix citric acid with water, put it in a metal vessel, and then we pressurize the vessel with CO2. And if you look at the figure on the right, what we're doing at about a pressure of 100 bar, this is, or a little less. So we're in the range of 750 to 12 or 1300 psi for the CO2 pressure, and we end up in this space in the phase diagram where it says supercritical fluid. Our temperatures are about 70 C, so that puts us about here. So we're in the supercritical regime. Other people will call this dense gas. And so the CO2, when it's brought to this pressure and temperature, acts like both a gas and a liquid. And that gives it very unique properties, and it enhances the extraction of the rare earths from these unconventional sources. And you can see on the right, we're able to do quite a bit better extracting with the ARC process as compared to a more conventional process, an acid-based process that's typically used in conventional mining. So higher extraction efficiencies enable us to start looking at potential, look at these coal ash resources, because in some cases we get extraction efficiencies depending on the coal ash of up to 80%. We're getting 80% of the rare earths out of the coal ash. Extraction efficiency turns out to be somewhat dependent on the type of coal. Some of the eastern coals, we see less extraction efficiency. Western coals, like the coals from Wyoming, we get much higher extraction efficiencies. So, one of the things that we're looking at through this process, of course, is assessing these resources, assaying them. What are going to be the best targets for metals extraction based on what's available in the starting material. Next slide. So we've started to think this through. This is really important at the end of the day. Is this going to be economic? And assuming we can recover a couple $100 of rare earths per ton per hour, with costs of $800 per hour, which includes labor, energy, consumables, and amortized capital equipment. These plants, we envision, will be fairly small. They'll be automated, but they'll be set up to do processing of large volumes. So with an assumption of a cost per hour at $800, we have a break even at about 4 tons an hour of fly ash processed, assuming that we were recovering $200 worth of rare earths. So what you see in the figure on the right, here's my math, by the way, Marty. We with these assumptions, you can see the lines cross at about 4 metric tons per hour. And the lines are income and costs. So we start to become potentially profitable above 4 metric tons an hour. If we can process 6 to 8 metric tons per hour of the fly ash, we have a great opportunity to not only recover these critical minerals, but make money doing it, while at the same time we're cleaning up what is becoming a significant environmental hazard in the United States. Next slide. So, in summary, there are substantial volumes of fly ash available. We have the opportunity, we believe, to mine and concentrate, rare earths, other transition metals which are likely to be present. Things like vanadium and cobalt and copper tend to show up in fly ashes. We're cleaning the fly ash. We're removing the valuable metals, but we're also extracting other things like the uranium and other potentially toxic metals. Occasionally, arsenic and selenium are present. And the clean fly ash then can be sold for construction materials. This is currently being done right now in the Southwest. There's a company called Salt River Materials Group that's based in Phoenix that makes fly ash cements and pozzolans. And so we have an opportunity to sell the clean fly ash at the end for construction materials. And the other thing that I think has value, it's a value that we have to consider, I think, more thoroughly than we have so far. But if we're cleaning these fly ashes up at sites where the power plants have significant liability, there's opportunities there, I think, to collaborate and develop a more robust value proposition for this whole process. And because the processing chemicals used are water and citric acid, which are environmentally benign, and CO2, and I know there are concerns about CO2 today and its effect on climate warming. In this process, we can recapture the CO2 post-extraction. So once we've finished the extraction of the rare earths from the mineral, we can release the pressure in the vessel and capture the CO2, and then separate it from the rare earth element rich extraction fluid, which at this point is water and citric acid complexing the target metals. So I will leave it there and await questions.
Okay. Thank you, Mark. That was very informative, coming from Sandia National Laboratories and all the work that they're doing at that end. We are almost out of time here, but I do have two questions that got texted over to me. So any one of you guys can take it, try to answer it as quickly as possible. I'll read them real quick. The first question was, what percentage of rare earth minerals are actually on tribal lands? The second question was, the helium in northeastern Arizona, just how much is there in that region? So if who was ever open, to take those questions, go for it. Keep it short.
This is Marty. I could help answer the first one relative to the question of how much is on tribal land. The short answer is no one really knows. There's just not a robust catalog of exploration work on tribal land, and that's something, as a mineral exploration company, we've made ourselves available to assist with in a responsible way. So it's an easy question to answer because there's not much of an answer. That's a catalog that needs to be developed, and we think there's opportunity there, but it needs to be done carefully, responsibly, and in partnership.
Yeah, quickly, I'll jump in and mention there's 7 coal plants in Arizona and New Mexico. A number of those are actually on tribal land, and with each one of those, there is a stockpile of fly ash associated with the power plant. So if you were, but as Marty said, nobody's done the full assessment of what the resource might be conventionally or unconventionally.
Well, I might just throw in one thing. I looked up the helium in Arizona before this presentation, although it wasn't part of my bill, but the two sites, Pinta Dome, and the other one I'm going to mispronounce, but Dinabikea, that's close, both in Apache County. And they were both, the exploration was done there in the 60s, in the 1960s. And there was some production of natural gas there, but it's a large field. It extends west of there quite a ways too. So there's considerable amount of helium there. Rare earth elements, though, probably are discoverable through the U.S. Geological Survey information that is available. It just hasn't been compiled, but it is available on water, for instance, on water resources on Indian lands. I've seen that, I know, and I think it could be developed. It's probably a rich field for somebody to pursue. Would you agree with that, Marty, or not?
Yeah, we've spoken to folks at USGS, and like things like Earth MRI and other exploration data isn't really available because that can't be done on tribal land without tribal permission. So, the data set is pretty lean. But if a particular tribe had a segment of property that they wanted to engage in the Earth MRI project, as an example, I know, especially the current administration is, pretty keen to lean into that and partner on that.
Okay, thank you, gentlemen. We'll turn it back over to Derek for his closing of the session.
Thank you, Steve, and thank you, everybody, for great overview on rare earth minerals. I think the big question that probably I had and we're trying to answer is what's available in any country. But I think for me, my takeaway from 3 presentations today is that, rare earth minerals and the supply or the demand that's ramping up will require the need for more supply here in this country for national security and economic security. And so tribes, if they choose to do so, and we believe, I believe in the reading that I'm seeing, that there is sufficient adequate supplies of the different materials that we talked about on reservations, in particular coal, fly ash, and those kinds of materials. But it's really up to the tribes and what their endeavors and plans are. And so, but as Steve and I have been indicating, the big emphasis for tribes is the ability to generate revenue so they can provide for the jobs and provide for their economies. And so we're hoping that the information here will be a start for those that are working at tribes or those that want to work with tribes, kind of open the door to look at these new possibilities. And so, yes, we're looking at, a net zero clean environment, but it's going to take a lot of resources to get there. So I want to say thank you, gentlemen, for making great presentations. As Alex said, this information is available online. Thank you, Sheila, for joining us. It's always a pleasure to have you. And Mike, as usual, thank you for this. And so on behalf of Sagebrush Hill Group, LLC, Steve Gray, and myself, we are very appreciative of USEA and, of course, the Department of Energy for allowing us to do this. And so we have one more session 2 weeks from now. And I misspoke last time, but our last session is going to be on ESG. And so we're going to try to bring it all together and look at, the environment, the social consequences and governance, of all this material. We'll try to wrap that into our last session for this series. So with that, I want to say thank you, everybody. And hopefully, if we didn't answer your questions, please feel free to email us through USEA and we'll try to get back to you. And for that, we'll say so long, everybody. Be safe on your travels and take care, everybody.
Thank you.
All right. Bye now.
Bye.